The deeper we dive into the mysteries of 3IATLAS, the more we find ourselves trapped in an endless cosmic maze. Humanity's sharpest eyes have already locked onto this interstellar visitor, as if that alone wasn't enough. Yet, just when the story seemed overwhelming, the sudden arrival of C-2025-R2 has made the unfolding drama feel more intense, more suffocating than ever before. On September 11, 2025, the Swan instrument aboard the Solar and Heliospheric Observatory, SOHO, spacecraft detected the presence of a new comet. Officially designated C-2025-R2 and initially nicknamed Swan R2, it had actually been within 30 degrees of the Sun from August 8th to September 13th, 2025. Yet, because of its extreme proximity to the Sun, most telescopes were unable to observe it. Calculations suggest it will reach perihelion in October 2025, passing at a distance of about 75 million kilometers from the Sun. What impressed astronomers the most was its striking appearance, a tail stretching 2.5 degrees across the sky, completely dwarfing the tiny one recently formed by 3IATLAS. By brightness and size alone, Swan R2 appears more than 100 times greater, hurtling straight toward the Sun. As it drew closer, Swan R2 erupted with blinding brilliance, glowing in shades of white and green. Surrounding it was not the usual cloud of icy debris, but rather a massive silver plasma shield, a living electromagnetic barrier strong enough to bend solar wind and deflect radiation. Its emissions were equally bizarre: plasma nickel, dense iron, carbon dioxide, and carbon monoxide, a chemical footprint that seemed almost artificial. Most astonishing of all, its core was measured to generate 10,000 gigawatts per second, 1,000 times more than 3IATLAS. And the greatest shock? NASA confirmed Swan R2 follows a strict orbital cycle, returning to Earth's neighborhood once every 22,554 years. Its sudden arrival, just as 3IATLAS was accelerating toward the Sun, seemed far too coincidental. In his latest paper, Harvard astrophysicist Avi Loeb posed a daring question: could the two objects share the same origin? Yet orbital analysis by expert Peter Veres ruled that out. Swan R2 emerged from the direction of Aquarius, while 3IATLAS came from Sagittarius, 2 points separated by tens of degrees in the sky. So why did they converge toward the Sun at nearly the same time? This has sparked dramatic speculation. Perhaps Swan R2 and 3IATLAS are not independent wanderers at all, but two parts of a far larger design: a mothership and a probe. Smaller and weaker, 3IATLAS could easily be a reconnaissance craft launched by the vast system that is Swan R2. Its perfectly timed 22,500-year cycle makes it feel less like coincidence and more like an intentional schedule. If so, its solar passage may not be a random orbit, but rather a kind of maintenance cycle, drawing in superheated plasma as fuel, recalibrating vast hidden sensor networks around the planets, or exchanging data with secret relay stations buried deep within the asteroid belt. And when comparing the energy outputs, the mystery deepens. Swan R2's core releases power thousands of times greater than 3IATLAS, a figure that defies every natural law we know. Perhaps Swan R2 and 3IATLAS are not just celestial phenomena for us to observe. They may be signals, messages written across the stars, reminding humanity that we are not alone in this universe. Strange overlapping signals kept hinting that 3IATLAS might be bending the solar wind itself. Just when Atlas seemed to be fading back into normality, its bizarre coma structures, unpredictable orbit, and unusual chemistry dismissed as rare coincidences. A shocking twist arrived. 3 separate solar observatories picked up perfectly synchronized anomalies, raising the possibility that Atlas might be anything but natural. At 0803 UTC on August 18th, SOHO detected a strange bow-shaped structure forming in the solar wind just downstream of Atlas's orbit. 2 minutes later, Parker's solar probe recorded a sudden, powerful spike in local magnetic intensity, accompanied by an abnormal gradient unlike anything in its baseline. Finally, at 8:11 UTC, MAVEN observed a deflection in high-energy particles. The coordinates it logged matched Atlas's trajectory down to the decimal point. For years, these missions have quietly monitored the Sun from vantage points scattered across the solar system. The odds of all three randomly recording the same event, at the same location, at the same time, are practically zero. Coincidence no longer holds weight. The discovery triggered an emergency meeting at NASA, uniting mission leads from SOHO, Parker, MAVEN, along with JPL's data directors. All possibilities of instrument error were ruled out. The data was real. The very idea that a cosmic rock could pierce, or even resist, the crushing force of the solar wind borders on the unimaginable. To achieve such a feat, an object must satisfy three strict conditions. First, a powerful magnetic field. Earth is the prime example, shielded by a vast magnetosphere, an invisible barrier that deflects most charged particles hurled at us by solar storms. Thanks to this defense, our atmosphere and surface remain intact despite the Sun's violent outbursts. Second, a thick atmosphere. It doesn't just absorb, but also weakens the onslaught of high-energy particles before they can reach the ground. Mars offers the cautionary tale. Once home to oceans and a dense atmosphere, the red planet lost its magnetic field. The solar wind stripped away its outer layers of air, leaving behind a barren, lifeless world. Third, sheer size and mass. Only giant planets can sustain an atmosphere and drive the molten metal core dynamics needed to generate a lasting magnetic shield. By contrast, small bodies like asteroids and comets, lacking both strong magnetism and protective atmospheres, are shredded by the solar wind. Their tails are stretched, twisted, or erased entirely during violent solar outbursts. And yet, 3IATLAS appears to defy all of these rules. Recall Gemini South's data. A massive tail was observed, making Atlas look increasingly like a normal comet. But here lies the paradox. If Atlas really were just a comet, it could never survive a direct plunge into the solar wind. Its icy surface should sublimate, its tail distorted, fragmented, or blown away completely by coronal mass ejections. In other words, comets don't cut through the solar wind. They are carved apart by it. So how can an interstellar comet do what every known comet in our solar system utterly fails to achieve? Three independent streams of evidence, three separate instruments, yet all converge on the same unavoidable conclusion. This interstellar object has generated an effect previously thought possible only around the giant planets. Still, the gap between raw data and scientific explanation remains. At JPL, caution dominates. Their stance: Atlas cannot possibly carry a magnetic field as strong as Earth's. It lacks a molten, spinning core capable of powering a dynamo. For them, the anomalies are nothing more than thin plasma clouds, blown around as solar wind collides with Atlas's dusty outer shell. But at MIT, a bolder theory has emerged. Some scientists suggest Atlas may have once drifted through the shockwaves of an ancient supernova. In doing so, it could have absorbed a colossal remnant of magnetic energy, enough to leave behind a magnetized shell surrounding its surface. If true, this fossil field might act like an invisible shield, allowing Atlas to bend the solar wind like a miniature planet. It sounds like science fiction, but it forces us to think differently. If Atlas truly carries the magnetic scar of a catastrophe millions of years old, then it isn't just a random passerby between the stars. It is a messenger, branded with the signature of cosmic events far beyond human reach. But this is only the beginning. 3IATLAS is not slowing down, it's accelerating. When it was first discovered, its velocity was around 61 kilometers per second. Now it has surged to 87 kilometers per second. To put that into perspective, at that speed, it would take just 74 minutes to travel from Earth to the Moon, so fast that even SpaceX's Starship, humanity's most advanced spacecraft, could hardly keep up. According to the latest orbital analysis, on September 26, 2025, 3IATLAS will swing past Mars at a distance of only 1.95 million kilometers, a razor-thin margin on the scale of the cosmos. At such close range, Mars's gravity could easily perturb its orbit. And with just an extra 10 kilometers per second boost, Atlas could tilt its trajectory enough to turn a near miss into a direct collision within mere weeks. In principle, any body passing close to the Sun, Jupiter, or Mars can have its path slightly altered by gravity. But those changes are usually tiny, accumulating slowly over time. Atlas, however, is writing a script unlike anything ever recorded. Studies show it is venting carbon dioxide at astonishing rates. Even more puzzling, its cyanide and nickel levels are surging, yet with no trace of iron. Its water content is shockingly low, just 1/8 the amount of CO2. But the most jaw-dropping discovery is this: a rhythmic release cycle, pulsing every 17 minutes with clockwork precision. Unlike the random outgassing typical of comets, Atlas seems to be firing controlled jets of gas, as if it were a spacecraft making course corrections. These perfectly timed bursts have produced a steady acceleration, nudging it closer and closer toward Mars's orbit. If this controlled propulsion continues, Atlas could skim within 50,000 kilometers of the red planet, closer than some of Mars's own tiny moons. Which means just a little more thrust could transform a harmless flyby into a deliberate impact. And most disturbing of all, it appears to be doing this with a propulsion system under intelligent control, behaving less like a comet and more like a colossal self-guided rocket. In such a scenario, the goal might not be destruction at all, but deployment. A perfectly calculated touchdown, placing some kind of device on the Martian surface without obliterating the planet. If true, this would mark one of the most enigmatic missions ever carried out in the history of the universe, a mission humanity is only now realizing it has the privilege to witness. So perhaps what we are witnessing is not a threat, but a message. A message delivered to humanity in the form of a massive interstellar object. Mysterious, dangerous, but purposeful. Could 3IATLAS truly be the emissary of an alien civilization? A reconnaissance craft conducting observations at the very edge of our solar system? Or are these anomalies simply nature's tricks, breaking every rule science thought it understood? The answer may soon reveal itself as Atlas draws closer to Mars than ever before. Until then, all of humanity can only watch, waiting for the historic moment when the final secret of 3IATLAS is unveiled. The brightness that we see coming from it, if it's just the reflection of sunlight from a solid surface, implies that it has a size bigger than Manhattan Island. That's 1,000,000 times more massive if it's a rock than the previous objects we saw. Avi Loeb, a famous professor at Harvard University, said, "The discovery of 3IATLAS has once again pushed us to rethink everything we thought we knew about the universe. Normally, comets develop tails that always point away from the sun. This happens because sunlight forces out tiny dust particles from the comet's surface. These particles are extremely small, roughly the size of a wavelength of light, and as they scatter sunlight, they create that glowing tail pointing away from the sun. But with 3IATLAS, scientists discovered something unusual: larger dust particles being released from the sunlit side of the object. These particles are much heavier than the tiny ones usually pushed away by sunlight. Because of their size, the bigger particles don't get blown away. Instead, they linger close to the comet and last longer, forming a snowline that actually points toward the sun. This is known as an anti-tail. What's even more fascinating is that this anti-tail was found to stretch about twice as far as the glow of scattered sunlight seen in directions either opposite or sideways to the Sun. This remarkable observation was highlighted in a recent study co-authored by Harvard's Avi Loeb, yes, him again, along with his brilliant colleague Eric Kito. Especially this discovery was made from Earth, where our viewing angle wasn't ideal. When the Hubble Space Telescope took a picture of this comet on July 21, 2025, the way we were looking at it was not the best for seeing this anti-tail clearly. The line from the comet to the Earth was almost the same direction as the line from the comet to the Sun, only about 10 degrees off. This means we were basically seeing the anti-tail almost from the side, which makes it look shorter than it really is. There's a math trick here. Because we see the tail at a sharp angle, the real length of the tail is actually much longer, almost 6 times longer, than what the picture shows. So if we had a spaceship that could hover right above the comet and look straight down the anti-tail toward the Sun, we'd see that this glowing part stretches out about 10 times farther than its width. This is a very big and surprising stretch of the comet's glowing dust, something scientists hadn't noticed before. It shows how weird and different this comet really is compared to most others. Are we alone? Probably not. Avi Loeb said, "This idea fueled Loeb's drive to ignite public interest this summer, following the discovery of the third mysterious interstellar object. It stands out for being unusually bright, following a strange trajectory, and being massive in size." Once again, Loeb openly speculated whether it could be a fragment of extraterrestrial technology. According to Avi's research, the nucleus of 3IATLAS could have a diameter of up to 46 kilometers, making it about 1,000,000 times more massive than the interstellar comet 2RAO, Borisov. On October 3rd, the high-rise camera aboard the Mars Reconnaissance Orbiter is set to capture images of 3IATLAS with a pixel resolution of 30 kilometers, offering the most precise measurement yet of the nucleus's size. While awaiting crucial data from the Mars Reconnaissance Orbiter, debate over the true size of 3IATLAS continues. Early estimates, including Avi Loeb's calculations, suggested a very large nucleus, but some scientists argue those numbers may be misleading. The bright, expansive coma surrounding the nucleus, measuring at least 348,000 kilometers, over 216,000 miles, in radius, can make the comet appear larger than it actually is. Because the coma contributes heavily to its brightness, many researchers lean toward smaller size estimates. Later, high-resolution images from the Hubble Space Telescope indicated a much smaller nucleus, likely between 0.3 and 5.6 kilometers, 0.2 to 3.5 miles. Other measurements, based on water vapor emissions, suggested a size around 5 kilometers, though these could be overestimates since much of the gas may be coming from the coma rather than the nucleus itself. The components of this coma also caught the attention. The plume of gas around 3IATLAS is composed primarily of carbon dioxide, 87% by mass, with traces of carbon monoxide, 9%, and water, most of the remaining 4%. It also features nickel without iron, as known to exist in industrially produced nickel alloys, and cyanide, both rising sharply with decreasing heliocentric distance. Like other comets, 3IATLAS also has a tail pointing away from the Sun. But this one is unusual. It appears as a very faint, broad tail stretching eastward, as seen in Hubble images from July 2025. This raises the question, is such a fuzzy tail enough to classify 3IATLAS as a comet? Some scientists say yes, suggesting it could be a dark comet, essentially a comet with little or no visible tail. However, Avi disagrees with that view, that it's an oxymoron because it's just like looking at an elephant and saying, that's a zebra without stripes. Okay, so when you say a comet without a cometary tail, the tail is the signature of a comet, Avi said. This perspective, combined with the earlier findings, is one reason why Loeb has been advocating for more openness to alternative explanations for interstellar objects like 3IATLAS, including possibilities that go beyond natural comets. His hypothesis is reinforced by a series of more unusual anomalies observed in this object. The retrograde trajectory of 3IATLAS is aligned with the ecliptic plane of the planets around the Sun to within 5 degrees, with a chance probability of 1 in 500. This is like flipping a coin 9 times in a row and getting heads every time, very unlikely by chance alone. This coincidence brings 3IATLAS to pass within several tens of millions of kilometers from Mars, Venus, and Jupiter. Such close encounters are rare for random interstellar objects. From an intelligent design perspective, such an orbit would be ideal for an artificial probe or spacecraft sent into our solar system. It can easily navigate within the planet region, observe multiple planets, and even attempt optimal maneuvers, such as a reverse solar orbit maneuver near perihelion for controlling its orbit. Avi Loeb's groundbreaking research has attracted the support of wealthy donors who have contributed funds to back his projects at Harvard's astronomy department. At the same time, he has his critics. Some dismiss his ideas as sensationalism, claiming he's simply seeking attention, leveraging generous donors, and using the buzz to sell more books. Loeb's response to such criticism, however, has been notably calm. "I don't really care what people think. Science is not about us lecturing the public what is right and or wrong. It's about a process by which we all learn together," Avi said. Loeb is now leading the Galileo project, which is setting up observatories across the country to track interstellar activity. He believes that discovering alien technology could represent the greatest breakthrough in human history. According to him, extraterrestrials might be much smarter than we are, could have bigger brains, could have artificial intelligence far beyond ours, and could know more about science. His strategy is simple. Just watch and listen. Loeb encourages other scientists to seriously pursue this line of research instead of dismissing it outright. When asked, "What if I'm completely wrong?" he calmly responds, "That's okay." For him, curiosity is essential. Without it, we'll never know. He believes that if something is out there, it would be a positive discovery, as humanity could learn from it. So what about you? What do you think of Avi Loeb's work on 3IATLAS and other mysterious interstellar objects? Is he truly pushing the boundaries of space science? Share your thoughts in the comments below. We often talk about Oumuamua and 3IATLAS, but have you heard of the second interstellar visitor, 2I Borisov? Back in August 2019, engineer Gennady Borisov was scanning the pre-dawn sky for comets with a telescope he built himself. In one frame, he noticed a small blurry object at the edge. Over the following nights, he confirmed that it was moving on a trajectory unlike anything seen from objects within our solar system. The discovery was soon confirmed by other observatories, and on September 24th, the International Astronomical Union officially designated the object as Interstellar Comet 2I Borisov. It became only the second interstellar object ever identified, following the asteroid 1I Oumuamua in October 2017. What made Borisov unusual was its highly hyperbolic orbit, meaning that after passing through our solar system, it would continue its journey into interstellar space. Such an orbit is possible only for an object traveling at an extremely high speed. 2I Borisov was moving at 30 kilometers per second as it approached the Sun. That's why it was confirmed beyond doubt as an interstellar object, because no local solar system body could reach such speeds. Analysis of the comet's light spectrum revealed much higher levels of frozen carbon monoxide relative to water than would be expected. The relative abundance of carbon monoxide was orders of magnitude higher in 2I Borisov than is normally seen in comets in the solar system. carbon monoxide turns from ice to gas at extremely low temperatures, minus 250 degrees Celsius. So it means that this comet formed and lived all the time in the area where the radiation of the host star was so diluted that the ice could survive. This indicates that the comet came to us after being ejected from the distant outskirts of some other planetary system. Before 2I Borisov, there was Oumuamua, first spotted racing through the solar system in October 2017. Ever since, astronomers have been working to unravel its mysteries. Traveling at nearly 195,000 miles per hour, Oumuamua was moving so fast that scientists had only a short window to study it before it vanished into interstellar space. Recent research suggests Oumuamua could be a fragment of a Pluto-like planet from another star system. Unlike comets, it showed no visible tail. Instead, it appeared as a long, cigar-shaped reddish rock. Dry, shiny, about as thick as a 3-story building, and half the length of a city block, tumbling through space in a puzzling motion. Oumuamua differed from comets in other ways too. It entered the solar system at a slower speed than expected. If it had traveled through interstellar space for over 1 billion years, like many comets, it should have been moving faster. It also experienced an extra push, a rocket effect, stronger than what comets usually get from ice evaporation near the sun. While some studies proposed condensed water ice as the driver of this motion, Arizona State University astrophysicists Stephen Desch and Alan Jackson concluded that solid nitrogen fit the data best. Its shiny surface resembled other nitrogen ice objects. In our solar system, Pluto and Saturn's moon Titan are mostly covered in nitrogen ice. So it's possible Oumuamua was once part of a Pluto-like world shattered in a collision in another planetary system. A similar process happened in our own Kuiper belt. Billions of years ago, Neptune's outward migration disrupted countless icy bodies, causing massive collisions among Pluto-like objects rich in nitrogen ice. If it happened here, it's reasonable to think it happens elsewhere. Researchers estimate that its encounter with the Sun stripped away about 95% of its original mass. Once again, the updates about 3IATLAS refuse to stop surprising us. Drifting silently through the vast, terrifying emptiness of space, this mysterious visitor has been keeping scientists on edge for more than 2 months. At first, it seemed destined to leave behind nothing but unanswered questions, just like Oumuamua. But now, clearer signs are beginning to reveal the true path of its journey. Is this simply another interstellar comet? Or could it be something far more unusual? Something hiding in plain sight? Let's find out right now. In early August, a report titled Extreme Negative Polarization of New Interstellar Comet, 3IATLAS, by Z. Gray et al., 2025, revealed the latest evidence about how 3IATLAS polarizes light compared to other objects, including solar system comets and even the previous interstellar visitor, 2I Borisov. The results were truly shocking. 3IATLAS exhibited an extremely deep and narrow negative polarization, reaching about minus 2.77% at a phase angle of 6.41 degrees. On top of that, its polarization inversion angle, the point where the polarization changes sign, was unusually low, only 17.05 degrees. So, what does this mean? It shows that the way light interacts with the dust and gas around 3IATLAS is completely different from anything seen in solar system comets, including 2I Borisov. It doesn't fit into either the high P or low P groups of comets. Instead, Atlas seems to exist outside all known classifications. This unique combination of a low inversion angle and a maximum negative polarization makes 3IATLAS the first known object in history to display such optical behavior. Many scientists now believe it could represent an entirely new population of interstellar bodies, something humanity has never encountered before. Normally, when we observe a comet, sunlight reflects off the dust and ice in its coma and tail, becoming polarized. In other words, the light waves vibrate more strongly in one direction. Depending on the viewing angle relative to the sun, each comet shows a polarization signature, like a fingerprint. But with 3IATLAS, the reflected light breaks all the rules. This suggests its dust and ice may be made of materials completely unfamiliar to science. Think of polarized light like waves on water. When the waves hit an obstacle, their direction changes. Light behaves the same way when it scatters off dust particles. But with ATLAS, that change is so unusual and so extreme that it looks nothing like any comet we've ever studied. To put it into perspective, comets usually fall into two groups: high P and low P, depending on their polarization curves. At small phase angles, the angle between the Sun, comet, and Earth, most comets show a typical broad and shallow region of negative polarization. But ATLAS is different. It shows a much deeper, narrower negative polarization curve, meaning the light is polarized more strongly and only over a very narrow angle. Its inversion angle is also lower, meaning the flip in polarization happens sooner than expected. The bottom line, 3IATLAS is the very first object ever observed with this bizarre polarization behavior, something seen in neither comets nor asteroids, making it one of the strangest interstellar visitors in history. The mysteries surrounding 3IATLAS don't stop at its strange polarization. Remember, its arrival sparked an unprecedented collaboration between two of humanity's greatest observatories, the James Webb Space Telescope and the Hubble Space Telescope. To understand just how extraordinary ATLAS really is, let's compare it to the two interstellar visitors we've met before. The first, Oumuamua, was discovered in October 2017. By the time it was spotted, it had already passed perihelion and was speeding back into interstellar space. At first, observers thought it was just a weird comet. But traveling at 87 kilometers per second, it was simply too fast to be captured by the Sun's gravity. Even stranger, Oumuamua showed non-gravitational acceleration, possibly from outgassing or solar radiation pressure. It spun like an asteroid, but had an unusually elongated shape, tumbling rather than rotating smoothly. And although its reddish surface resembled objects from the outer solar system, it lacked the glowing coma we'd expect from a comet near the Sun. All of this fueled debates. Was it natural or even artificial? Unfortunately, because it was moving so fast, Oumuamua left the solar system quickly, leaving scientists with only limited data, and even bigger questions about what interstellar objects might really be. 2 years later, in 2019, came the second visitor, 2I Borisov. Unlike Oumuamua, Borisov looked almost exactly like a typical comet, complete with a tail of dust and gas. That allowed scientists to study it in far more detail. With an orbital eccentricity of 3.36, it clearly wasn't bound to the Sun's gravity, confirming its origin from deep interstellar space. But 3IATLAS is different. Its strangeness doesn't stop at a missing coma, non-gravitational acceleration, or comet-like features. Beyond its unusual polarization, ATLAS displays a whole series of anomalies that have left scientists puzzled about where it really came from. The first red flag appeared the moment astronomers began tracking its orbit. Unlike objects in our solar system, ATLAS travels on a retrograde path, moving opposite the direction of the planets. Even more astonishing, its trajectory lies almost perfectly along the ecliptic plane, deviating by only about 5 degrees. The odds of this alignment happening by chance? Roughly 1 in 500, enough to make researchers stop in their tracks. And that's not all. Calculations show that ATLAS's orbit will intersect with those of Mars, Venus, and Jupiter, 3 of humanity's most studied worlds. While it poses no threat of colliding with Earth, something remarkable will happen at perihelion. Atlas will pass behind the Sun, almost as if hiding from our view. Even more extraordinary, at that exact time, Earth, the Sun, 3IATLAS will line up in a perfect straight line. And only when its journey through the solar system is nearly complete, on its way back into the void, will Atlas swing closest to our planet, about 1.8 astronomical units, or 270 million kilometers away. Another anomaly that cannot be overlooked is the size of 3IATLAS. Current best estimates suggest its nucleus spans nearly 46 kilometers in diameter, a colossal figure compared to previous interstellar visitors. Earlier data from the Hubble Space Telescope only allowed astronomers to set an upper limit of about 5.6 kilometers, 3.5 miles, with some models suggesting it could be as small as 320 meters, 1,000 feet. Yet these figures remain only estimates, based on observational modeling rather than definitive measurements. One thing, however, is certain. Compared to its predecessors, Oumuamua and Borisov, 3IATLAS appears to be vastly larger, adding yet another layer of mystery to its true nature and origin. The third anomaly baffling researchers is Atlas's anti-tail, captured in images from the Hubble Space Telescope. Normally, a comet's dust tail always points away from the Sun, pushed outward by solar wind. But with Atlas, the dust tail strangely points toward the Sun instead. Some scientists propose this could be caused by unusually large, heavy dust grains in its tail, making them appear to resist solar wind pressure. However, the most recent observations from the Gemini South telescope revealed something even more intriguing: the faint emergence of a traditional comet-like tail. So, what exactly is happening here? That question brings us to the fourth and perhaps most crucial anomaly: the chemical composition of 3IATLAS. To truly make sense of its unusual orbit, its massive size, and its anti-tail, we must first understand what this object is made of. High-resolution observations from modern telescopes have shown that Atlas possesses a coma unlike any local comet. Surrounding the nucleus is a dense envelope dominated by carbon dioxide, making up 87% of its mass, with smaller fractions of carbon monoxide at about 9% and only 4% water. More strikingly, the gas column contains significant amounts of cyanide and nickel without any iron, a composition entirely unlike comets in our solar system. Measurements also reveal that as 3IATLAS approaches the Sun, both cyanide and nickel levels rise dramatically. This unusual mix has led astronomers to suspect Atlas might not be just another interstellar comet, but possibly the first representative of an entirely different class of interstellar bodies, never before recorded by humanity. This chemical behavior may also explain the appearance of its anti-tail. As Atlas nears the Sun, intense sublimation drives larger ice particles outward, allowing them to travel farther before fully vaporizing. This effectively stretches the snow line, the region where ices can survive, closer toward the Sun. Because these larger ice grains are less affected by solar wind, they remain on orbits closer to the nucleus, forming the backward-facing dust structure we see. In other words, Atlas's anti-tail likely forms when large ice grains, propelled by CO2 sublimation, travel sunward rather than being blown away like in ordinary comets. This creates a rare forward-pointing dust stream, a feature seldom seen among comets. And perhaps this very process also explains the recent emergence of a more traditional tail, as those once massive ice grains continue to sublimate under increasing solar heat. They grow lighter until finally they can be swept back by the solar wind, mimicking the behavior of a conventional comet. If this interpretation holds true, then evidence may be leaning more strongly toward Atlas being a natural interstellar comet, though one unlike any we've ever encountered before. But no matter what, the evidence we currently have is still not enough to determine the true origin of this mysterious object. All eyes are now locked on the upcoming milestone, October 3rd, just 21 days from now, when 3I-ATLAS will make its closest approach to Mars before reaching perihelion with the Sun. At a distance of just 0.2 astronomical units, about 30 million kilometers from Mars, scientists are preparing for a new wave of close-up observations of this interstellar visitor. At that time, researchers plan to take advantage of the probes already orbiting Mars to track 3I-ATLAS. NASA's Mars Odyssey, Mars Reconnaissance Orbiter, MAVEN, and the ExoMars Trace Gas Orbiter are all capable of doing so. Meanwhile, Professor Avi Loeb of Harvard University has recently suggested that the HiRISE camera, the high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter, could potentially capture the first-ever close-up image of 3I-ATLAS on October 3rd, 2025. With a resolution of 30 meters per pixel, HiRISE may not be able to reveal the full shape of the comet, but it could constrain its brightness and help measure the true size of its nucleus. This will allow scientists to confirm whether it is really 46 kilometers wide, or perhaps smaller, or even larger. And if the comet dominates without a clear bright point, we'll gain crucial insight into the actual nucleus of this interstellar object. At that moment, the so-called Loeb scale may well be redefined. Could 3I-ATLAS prove to be just a bizarre comet, or is there truly something more, something intentionally hidden? One thing is certain. Fascinating discoveries lie ahead, and we'll be here to cover them all. So fasten your seatbelts and stay tuned as we follow this mystery together. On September 4th, an incredible cosmic event happened. NASA's Psyche spacecraft made its closest approach to an interstellar comet called 3I-ATLAS, and we've got the stunning details to share with you. Stick around because this is one for the space history books. So let's start with what we're looking at here. This breathtaking image, captured by the Psyche spacecraft, shows the interstellar comet 3I-ATLAS. Yesterday, at around 0.301 astronomical units from the comet, that's about 45 million kilometers, Psyche got up close and personal. This wasn't planned, folks. Psyche was originally headed to study a metal-rich asteroid named 16 Psyche, but it's now part of an exciting NASA campaign to observe this rare visitor from beyond our solar system. So how did Psyche get involved? This spacecraft, built with cutting-edge tools like an imager and magnetometer from Arizona State University and NASA's Jet Propulsion Laboratory, was already on its way to the asteroid belt. But when 3I-ATLAS swung by, NASA saw an opportunity. Psyche's adaptability shines here. It's using its high-tech gear to study this comet, adding a new chapter to its mission. Pretty cool, right? This observation is a big deal for science. Interstellar objects like 3I-ATLAS challenge our understanding of how isolated our solar system is. Studies like those from Dr. Karen Meach and colleagues back in 2017 suggest these visitors could carry clues about other star systems, or even dormant spores, though that's still a theory. With Psyche's data, we might learn more about the comet's composition, structure, and how it got here. Previously, 4 of the world's most powerful telescopes, the James Webb, Hubble, the Very Large Telescope, and NASA's SpaceX mission, teamed up to study a mysterious interstellar visitor. Each one captured a unique perspective of 3I-ATLAS, and together they pieced together one of the most complete pictures we've ever had of such a distant guest. On August 6th, the James Webb Space Telescope focused its near-infrared spectrometer on 3I-ATLAS, aiming to decode the chemical makeup of its coma, the hazy cloud surrounding its solid core. What it revealed left scientists stunned. Unlike ordinary comets, which are typically dominated by water vapor, 3I-ATLAS turned out to be saturated with carbon dioxide. In fact, its carbon dioxide to water ratio is an astonishing 8.1, the highest ever measured in any comet, with no other object even close. Even more puzzling, ATLAS is missing the usual suspects like carbon monoxide in the amount scientists expected. This means it doesn't behave like the comets we're used to, which shoot out jets and plumes in predictable patterns. Instead, Atlas seems to have formed in an environment utterly unlike our own solar system. Perhaps near a carbon dioxide ice line, in its parent star's planetary disk, or maybe in a region blasted by such intense radiation that water was stripped away completely. The chemistry is so alien that researchers are now questioning whether our models of comet formation can even apply to these interstellar wanderers. Atlas isn't just another comet. It's rewriting what we thought we knew about how worlds and systems are born. Just like James Webb, NASA's SpaceX mission spotted a massive halo of carbon dioxide gas surrounding 3IATLAS, stretching an incredible 348,000 kilometers into space. Even more intriguing, it detected water ice locked inside the comet's nucleus, hinting at a complex and layered history. Then came Hubble. On July 21st, the legendary space telescope snapped the sharpest images we've ever seen of an interstellar comet. The pictures revealed a solid, icy core wrapped in a teardrop-shaped coma of dust, blasted off as sunlight warmed the surface. Scientists estimate the nucleus could be anywhere from 320 meters, 1,000 feet, to 5.6 kilometers, 3.5 miles, across, but based on how fast it's shedding dust, they suspect it's probably less than a kilometer wide. More interestingly, the dust tail of 3IATLAS is unique as dust is being ejected in the direction toward the Sun, rather than away from it as in typical comet tails. Meanwhile, the Very Large Telescope in Chile added a twist to the story. It detected cyanide gas, common enough in comets, but also something far stranger: nickel without iron. That's bizarre because, in nature, nickel almost always appears hand in hand with iron, bonded together in alloys like those inside meteorites or planetary cores. Finding nickel alone suggests an entirely new chemical process we've never witnessed before. All of these points lead to one conclusion: 3IATLAS isn't just another interstellar rock. Its chemistry is unique, perhaps forged in the heart of ancient stars or in regions of the cosmos enriched with heavy elements. It's a cosmic messenger carrying secrets of worlds and stellar nurseries, unlike anything we've ever known. While Earth-based telescopes have given us an incredible head start in understanding this third known interstellar object, getting up close to 3IATLAS is the real game-changer. On October 3rd of this year, Atlas will make its closest approach to Mars. Just 30 million kilometers, 18 million miles away. That's dramatically closer than its approach to Earth in December 2025, when it will still be a distant 270 million kilometers, 168 million miles out. This close pass means Mars orbiters will have a front-row seat to capture sharper, more detailed images and precise measurements. From Earth's perspective, there's a big challenge. When 3IATLAS swings closest to the Sun, it's perihelion, and even during its closest Earth flyby, the comet will be hidden behind the Sun, making observations nearly impossible from here. But Mars orbiters will have a clear line of sight, perfectly positioned to study the comet during this critical moment. ESA's Mars Express, the ExoMars Trace Gas Orbiter, and NASA's Mars Reconnaissance Orbiter are all armed with advanced instruments capable of high-resolution imaging, chemical analysis, and spectral mapping. These spacecraft can reveal Atlas's composition, structure, and activity in a way no Earth telescope can. They'll be able to detect gases, dust, and perhaps even organic compounds or frozen water, materials that may have formed in a completely different star system. And it's not just Mars doing the heavy lifting. Farther out, missions like ESA's Jupiter Icy Moons Explorer and Psyche spacecraft might also catch glimpses of Atlas around the time of its perihelion, adding even more perspectives to the puzzle. Piece by piece, these observations will build the most complete picture yet of this ancient traveler, believed to be billions of years old, and possibly born in another corner of the galaxy. By studying it, we may uncover vital clues about planetary systems far older than our own and the cosmic ingredients that shaped them. Of course, even with Mars getting the best seat in the house, observing 3IATLAS still comes with plenty of challenges. First, there's the issue of distance. Yes, Atlas will pass much closer to Mars than to Earth, around 30 million kilometers. But that's still incredibly far. In the meantime, the Mars orbiters like ESA's Mars Express and the ExoMars Trace Gas Orbiter just orbit at altitudes roughly between 250 to 400 kilometers above Mars. There is clearly a huge gap here. Think of it like trying to snap a detailed photo of a speck from thousands of miles away. Even with advanced cameras, it's tough to get a truly close-up view. Because of this distance, the comet also appears faint. It doesn't shine brightly, which makes it harder for instruments to pick up clear signals. On top of that, the dust surrounding the comet can scatter or block light, hiding its icy core from view. Then comes the Sun. Mars orbiters depend on sunlight to take images, but the comet's position relative to the Sun can complicate things. The Sun's glare can easily wash out a faint target like Atlas, and the spacecraft needs just the right angle between Mars, the comet, and the Sun to get good shots. Speed adds another layer of difficulty. Atlas is racing through space at 600 times faster than the fastest racing car in the world, meaning Mars orbiters only have a short window to capture data. If the timing isn't precise, the best chances for observation could slip away. And finally, the instruments themselves. Mars orbiters are built to study Mars, its surface, atmosphere, and geology, not fast-moving interstellar visitors. Their cameras and spectrometers aren't optimized for faint comets, so scientists have to stretch the limits of the technology. Put all of this together, and watching 3IATLAS from Mars is a bit like trying to spot a firefly in the middle of a bright sunny day. Difficult? Absolutely. But that's exactly why every piece of data gathered will be so valuable. Even the smallest clue can unlock secrets about this mysterious traveler from another star system. Fortunately, many of these challenges can be tackled by applying lessons learned from past encounters between Mars and comets. One of the most significant examples was Comet C 2013A1, better known as Siding Spring, which made a dramatic pass by Mars on October 19, 2014. This was a once-in-a-lifetime opportunity for scientists to study how a comet interacts closely with a planet other than Earth. Siding Spring skimmed past Mars at just 140,000 kilometers, 87,000 miles, an incredibly close call in cosmic terms. At first, there were real worries that the comet might collide with Mars or even endanger the orbiting spacecraft. Luckily, it missed, and instead of disaster, the encounter delivered a treasure trove of data. Measurements revealed that Siding Spring's nucleus was much smaller than expected, somewhere between 400 and 700 meters wide. That's less than half a kilometer across, tiny compared to early estimates. Yet, even a comet that small created a massive scientific impact, showing just how valuable these close encounters can be for preparing to study 3IATLAS. For example, how to position Mars orbiters to both protect themselves from possible cometary dust and study this unique event scientifically. To protect the spacecraft, engineers adjusted their orbits so that during the period of highest dust activity, shortly after the comet's closest approach, they were shielded by Mars itself, staying mostly on the planet's far side. On the surface, rovers were naturally protected since the Martian atmosphere burned up incoming dust particles. The scientific payoff from this careful maneuvering was huge. Instruments detected a sudden spike in metallic ions and dust pouring into Mars's upper atmosphere. The comet's debris, rich in elements like magnesium, iron, sodium, and nickel, triggered a meteor shower about 1,000 times stronger than the typical meteor showers seen on Mars. Even more fascinating, the comet's magnetic field stirred up intense turbulence in Mars's already weak magnetic environment, lasting for several hours after the flyby. These observations gave scientists rare insights into how comets can affect planetary atmospheres and magnetospheres. Imaging also played a crucial role, allowing researchers to refine measurements of the comet's nucleus size, study its surface properties, and track how its activity evolved during the close encounter. This event set a powerful precedent for how to study interstellar visitors, like 3IATLAS, while keeping spacecraft safe. In addition, the comet's impact on the Mars spacecraft was noticeable. The orbiters experienced increased atmospheric drag as the comet's gases altered the upper atmosphere, slightly shifting their orbits. To minimize risks, mission teams carefully planned operations to shield the spacecraft from possible dust damage during the comet's closest approach. This encounter ultimately proved that Mars can be an invaluable platform for studying comets and their influence on planetary environments. It demonstrated both the scientific rewards and the risks of close comet flybys, while also preparing scientists to observe future visitors with greater confidence and precision.
We've got some fresh images of 3IATLAS, a third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live.
In the great tradition of humanity's quest to conquer the unknown, a new cosmic traveler has arrived. 3IATLAS is beckoning us to witness the cosmic evolution unfolding in real time. As 3IATLAS emerged from the outer darkness in early July 2025, its dust tail was barely a whisper, faint, broad, and pointing away from the sun. That's classic solar radiation pressure at work, pushing dust particles outward into space. Around this time, subtle cometary features began to emerge, including a hazy coma with a tail-like extension. Things were still pretty fuzzy because at that time, the comet was still very far from the Sun, 3.5 times the distance between the Sun and Earth. So when 3IATLAS drew closer to perihelion, the real story began. Fast forward to late August, powerful eyes like the Gemini South Telescope captured a much bigger story. The comet's tail had extended to about 56,000 kilometers. That's roughly 30 arcseconds in angular length, growing longer and clearer as the sun's heat intensified. This tail growth lines up perfectly with a surge in solar heating, which causes the comet's icy surface to sublimate and eject more dust. As we entered September, fresh images revealed the tail expanding rapidly, a sign that 3IATLAS is shedding more particles than ever before as it bathes in solar radiation. This evolving tail is a live show of cometary activity, evolving over weeks and months as it races toward perihelion. Surprisingly, the comet's tail not only expanded dramatically but also with incredible precision. Unlike natural comet tails, which are often messy, twisting, bending, and scattering unpredictably depending on the changing conditions of the solar wind and radiation, 3IATLAS's tail is broad, clean, and sharply defined. Instead of random gas streams spewing unpredictably, the tail extends like a smooth exhaust pipe, lengthening in distinct stages, as if it were purposefully self-regulating. What's even more intriguing is that this tail is pointed along a path that will bring the comet very close to Mars. In fact, Harvard astrophysicist Avi Loeb has proposed a fascinating idea. What if this tail isn't just a chaotic result of melting ice but actually functions like a thruster? A controlled exhaust stream pushes the comet along its carefully tuned trajectory. In other words, the tail could be acting more like a propulsion system than just natural comet outgassing. In addition to its dust tail, the comet also displays a striking dust plume that points directly toward the sun. This phenomenon occurs because the sunlit side of the nucleus experiences stronger sublimation of its icy materials. As these ices vaporize, they release streams of dust particles that shoot outward in the sun's direction, creating a brilliant fan-shaped extension of the coma. Sublimation of volatile ices is, in fact, the core engine behind cometary activity, fueling both gas and dust emissions. In theory, this means every comet has the potential to generate such sun-facing plumes, since sunlight consistently lifts particles from the illuminated surface. Yet in reality, only a select few comets, such as 3IATLAS and the distant oddity C/2014 UN 271 Bernardinelli-Bernstein, have displayed such prominent, visible plumes aimed sunward. This rarity pushes scientists to rethink certain aspects of cometary physics, hinting that the forces driving dust ejection and plume formation may vary widely depending on a comet's makeup, internal structure, and surrounding conditions. So what makes 3IATLAS develop such an unusual feature? A bright dust plume pointing directly toward the sun. We could find the answer in the facing sun dust plume with more material concentrated. By studying this plume, astronomers can deduce the comet's composition and the proportions of its key components. The findings are remarkable. Spectroscopic data from the James Webb Space Telescope and other instruments reveal that 3IATLAS is venting about 129 kilograms of carbon dioxide every second, around 8 times more than the water vapor it releases. This exceptionally high carbon dioxide to water ratio is almost unheard of in other comets. As a result, the comet produces an immense carbon dioxide plume that extends roughly 350,000 kilometers into space, nearly spanning the distance from Earth to the Moon. Alongside this, smaller amounts of carbon monoxide, water, and trace compounds are also present in the plume. Such a carbon dioxide-rich nucleus suggests that 3IATLAS may have formed near the carbon dioxide ice line in its original protoplanetary disk, or it may have undergone unusual chemical processing during its long solitary journey through interstellar space. Interestingly, the massive jet of carbon dioxide gas from 3IATLAS didn't behave the way scientists expected. In fact, it showed contradictory traits. Based on calculations, the solar wind, a constant stream of charged particles from the sun, should have pushed the jet backward, shortening its reach into space. In other words, models predicted that the plume should appear smaller and more compact. Instead, observations revealed the opposite. The jet stretched much farther than expected, growing larger than any of the simulations had suggested. Yet at the same time, the jet turned out to be physically too small and too weak to propel material all the way from the comet to Mars during its flyby. Its power is estimated to be about 100 times too low to make such a transfer possible. This leaves scientists with a puzzle. The jet is too extended to be normal, yet too weak to account for Mars-related effects. This puzzle tells scientists that the comet's jet and the cloud of gas and dust around it, called the coma, must be more complicated than we thought. Maybe something else is happening, like magnetic or plasma effects, that make the jet look big, even though it's not powerful. Or maybe the stuff seen near Mars isn't coming directly from the comet's jet at all. Typically, outgassing of this intensity would cause a comet to wobble or drift unpredictably under the force of the jet. But in the case of 3IATLAS, the activity appears remarkably stable, and the comet continues to travel along a well-defined, predictable orbit. This unusual steadiness is part of what makes 3IATLAS such a scientific enigma among active comets. As mentioned earlier, carbon dioxide and water aren't the only components present in 3IATLAS coma. In July 2025, the Very Large Telescope detected emissions of atomic nickel vapor within the coma. The discovery of nickel in the nucleus sheds light on some of the comet's unusual traits, particularly its brightness. What stands out is that nickel vapor was observed at levels higher than in typical solar system comets, and notably it appeared without the usual accompanying iron. This points to unique chemical and physical processes unfolding on or near the comet's surface. Nickel-bearing compounds could be enhancing the comet's brightness by altering how its dust and coma particles interact with light. The coma itself is described as dust-rich and red, meaning it reflects more red light, which influences its overall brightness as seen from Earth. Furthermore, the presence of nickel-based organics or tiny nanophase particles may be boosting sunlight scattering, amplifying the comet's visible glow. The release of nickel vapor in 3IATLAS appears to be driven by temperature-activated or photochemical processes, mechanisms not typically observed in standard comets. This points to a direct link between its unusual chemistry and the changes in its dust, gas emissions, and brightness. As the comet moved closer to the Sun, scientists noticed that the outflow of nickel gas didn't simply rise at a steady pace. It accelerated rapidly, like a snowball gaining speed and mass as it rolls downhill. These bursts of nickel emission lined up with periods when the comet grew brighter and when its coma, the glowing cloud around it, shifted in both size and shape. The faster the nickel vented, the more intense the comet's glow became, and the more its coma and tail transformed. This strong correlation shows that nickel is a key factor behind 3IATLAS's dynamic brightness variations and its distinctive dusty red-colored coma, setting it apart from the behavior of most solar system comets. The brightness of 3IATLAS makes it especially challenging for scientists to pin down its actual size. Normally, astronomers estimate comet sizes by measuring the brightness of the coma at different distances from the nucleus, and then fitting that data to a brightness function. By mathematically subtracting the coma's contribution, they can isolate the nucleus's brightness and use that to calculate its size. But in the case of 3IATLAS, most of the light we see doesn't come from the solid nucleus. It comes from its sprawling coma. This makes the separation process tricky and prone to error. If the coma's brightness isn't carefully removed, the nucleus can look far larger than it really is. In fact, early estimates put the comet's size between 10 and 20 kilometers wide, based solely on brightness. Later, with sharper data from observatories like the Hubble Space Telescope, scientists were able to refine their models and subtract the coma's light more accurately. These improved calculations suggest the nucleus is much smaller, likely under 5.6 kilometers across, and perhaps even as tiny as just a few hundred meters. The mysteries surrounding 3IATLAS continue to push scientists toward deeper observation. On October 29, 2025, the comet will reach perihelion, its closest point to the Sun, at about 1.36 astronomical units, roughly between Earth's and Mars's orbits. This will mark its period of peak brightness and strongest activity. However, it will be hard to observe from Earth at that time because it will lie close to the Sun in the sky, entering solar conjunction. Before that, on October 3, 2025, 3IATLAS will pass within about 30 million kilometers of Mars. This flyby creates a rare opportunity for Mars orbiters, such as ESA's and NASA spacecraft, to study the comet up close, potentially capturing detailed imagery and collecting valuable data on its composition and activity. From July to September 2025, the comet can be spotted after sunset. But as it nears the Sun, its visibility from Earth will shrink, limited mainly to equatorial regions. After perihelion, it should reappear in the morning sky in November, gradually fading as it drifts farther from both the Sun and Earth. In the meantime, a range of powerful telescopes, including the James Webb Space Telescope, Hubble Space Telescope, Very Large Telescope, Gemini South, and the new Vera C. Rubin Observatory, are actively monitoring 3IATLAS. Their studies focus on determining its size, composition, patterns of gas and dust release, and the dynamic transformations in its coma and tail. These ongoing and future observations are expected to uncover more about the chemistry of its nucleus and coma, provide critical tests for theories about interstellar objects, and deepen our understanding of cometary activity driven by unusual volatile makeups, particularly cases